All right. So, starting at the beginning, I'm just going to keep using this same checklist over here, going in this order, so hopefully like the repetition kind of helps. So first thing I'm going to do is factor the numerator and the denominator when possible. So what I see for that top is I can definitely factor the numerator by factoring out a 6. So I'm dividing a 6 out from both. And for the denominator, it's going to be a -4 and a +1, okay? So factor the numerator and denominator when possible. State the restrictions, use them for the domain, okay? The restrictions are x cannot be -1 and 4, right? If I'm setting the bottom equal to 0, -1 for the x plus 1, +4. So I need to, for my domain, state that x can be anything in the world except those two numbers. So this is like a 3-part domain. -∞ to whichever one you hit first. And then it's going to break because it can't be -1. Then it'll still be at -1, just not exactly on it, to 4. And then it's going to break, and then you're 4 to infinity. I didn't even look at the graph, right? I know that that's what it's going to be. Now eventually I'll look at the graph and I'll show you that's what it is, but that's what that means. So factor the numerator and denominator, state the restrictions, use them for the domain. Cancel out matching factors, use for whole. Whole is what we're going to talk about today, but nothing matches, so it didn't matter anyway, so it's not applicable. Find vertical asymptote by setting the denominator equal to 0. So for the vertical asymptote, really I'm kind of doing the same thing that I did for the restrictions and for the domain. My vertical asymptote is x equals -1 and 4. The same values. All of that is coming from the denominator. What a vertical asymptote looks like is a vertical line going through those values. And when we're done this problem, I'll show you the big picture of the graph and like what that does for the graph. All right. So that's my vertical asymptote. Vertical asymptote is an x equals equation, and it's a vertical dotted line. All right. Find the horizontal asymptote or slant. Yesterday we talked about how we get one or the other. Okay. So find the horizontal asymptote or the slant by doing the highest power in the numerator divided by the highest power in the denominator. So for this problem, the highest power in the numerator divided by the highest power in the denominator is 6x over x squared. One of the x's cancels out in the top, or the only x cancels out in the top and one cancels out in the bottom. When you are left with a number divided by x, so like when the top has an x and the bottom has an x squared, that's a horizontal asymptote of 0. So my horizontal asymptote here is 0. And if you have a horizontal asymptote, you don't have a slant. You either have one or the other. And then at the very end of class yesterday, I told you that whatever your horizontal asymptote is the same thing as your end behavior. So if my horizontal asymptote is 0, then my end behavior is 0 too. I don't even need the graph. Some of you are good at reading the graph for end behavior, and if you're good at that, then keep doing that, but you don't need to do that here. The horizontal asymptote of 0 looks like this. All right, so all of the blue pieces work together and all of the red pieces work together. And that's true for all of these problems, no matter what they look like. So just to kind of give you the big picture here, this is what this graph looks like. I typed it into my calculator. I have these ones shut off. All right, so this is the graph. I typed it in and I hit graph. And now I know like the left-hand region that was broken up by my asymptotes looks like this. The middle region has this upside down U, and the left region looks like this. So in terms of my graph here, there was some U shape happening in here. I think this was like this, right? You can see like the asymptotes break that up for me, so when I do that sketch, I know exactly like what part of the graph it will go in. All right, let's look at the next one. I'll try and do this one a little quicker. I can't factor anything though, right? 2x plus 1 doesn't factor. If you try to solve it, you get a negative discriminant. So we'll go restrictions. If I can't factor the denominator, then my restrictions would come from trying to solve this. But if you subtract 1 and you divide by 2, you can't take the square root of the negative number, so you can't solve the bottom, so there are no restrictions. And if there aren't any restrictions, what do you think the domain is? No restrictions. All reals, right? Negative infinity to positive infinity. If there aren't any restrictions, then there aren't any vertical asymptotes either. They are the same thing. A restriction and a vertical asymptote go hand in hand. So all of those pieces work together. Horizontal asymptote, I'm looking at the 3x squared over the 2x squared. And what happens here is the x squareds cancel out and leave me with 3 over 2. So when that happens, then your horizontal asymptote is a number. In this case, it's 1.5, or you can leave it as 3 over 2. If you have a horizontal asymptote, you don't have a slant. If you have a horizontal asymptote that's 0 or a number, that number is your end behavior. So the blues work together, the reds work together. In terms of this graph, I don't have any vertical asymptotes to draw in. My horizontal asymptote is somewhere between those. So I have that break. And that's really it. I only have a vertical break. So trying to get a bigger picture of this. This is what this graph looks like. And now I know at least where it's leveling off at. And it looks like it's got a U shape right at 0. All right, so that the asymptote gives me a more accurate sketch. We okay with that one? Now we left before we were really able to talk about end behavior of something that's a slant. So slant is what we did yesterday. This one has a slant. So we didn't really get a chance to talk much about the end behavior of this slant before you left yesterday. So first thing I'm going to do, factor the numerator and denominator. This doesn't factor, right? -4 adds to 1. So I don't think we can factor that. So I can't factor anything. So now I want to state the restrictions. X cannot be -2. Remember, because if the denominator is a 0, then everything's going to get an error. So instead of being a 3-part, it's just going to be a 2-part, because I'm just going to skip over -2. So negative infinity to -2, -2 to infinity. And all of that comes from factoring. I can't fit this. You guys get the idea? That's supposed to be an infinity. It's just kind of squeezed. So -2 to infinity. Domain and vertical asymptotes are the same. A restriction is a vertical asymptote. So there's a vertical asymptote here at -2. Here's what that looks like. When you go to do the horizontal asymptote here, x squared over x, one of the x's up top cancels and the x on the bottom cancels. And when you're left with just x, we call that a slant. So this does not have a horizontal asymptote, it has a slant. And yesterday we said to figure out what the equation of the slant is, we do synthetic division. We're going to do synthetic division on the opposite of the denominator. So -2 in this case, on your vertical asymptote essentially. And then you're using the coefficients of the numerator. So this is a 1, this is a 1, this is a -4. I want a linear equation. It only takes 2 numbers to make a linear equation. So I don't need the third number, right? That's called a remainder, and we won't need the remainder. So we're just doing synthetic division on the first 2 numbers. So my slant is x minus 1. 1x minus 1. Taking the coefficients of the solutions. What that looks like on the graph, you plot the y-intercept of negative 1, and then you go up 1 over 1. And I'm just continuing that pattern for the whole length of the graph. All right, so that's what my slant asymptote looks like. And you'll see the big picture here is when I hit graph for this, my graph kind of rides along the vertical asymptote and the slant and creates this image. So it looks like that, right? I don't know that without looking at the calculator. Eventually you will. We're gonna add some more pieces that you'll be able to get that graph without putting it in the calculator. But for now, you can get that idea. But the asymptotes help you do the sketch. Now, end behavior. We didn't talk about this part yesterday. We ran out of time. End behavior of a horizontal asymptote is really easy. If your horizontal asymptote's 0, your end behavior is 0. If your horizontal asymptote's 1.5, your end behavior is 1.5. I don't have a horizontal asymptote, I have a slant. Your end behavior of a slant is the same as the end behavior of the slanted equation. So when I'm looking to find the end behavior of this one, all I need to think about is the linear line I drew. All right, that's the slant. So the end behavior of my real equation, which is this long big one, has the same end behavior as that diagonal line. So think about the left side of this diagonal line. If I were to continue to draw the left side, I would be going down. So the left-hand end behavior is negative infinity. The right-hand end behavior, if I were to continue to draw this would go up. So the right-hand behavior is positive infinity. If you have a slant, your end behavior should be the infinities. Okay, so if you're a memorizer, then there it is, okay? Otherwise, you're just looking at the slanted line rather than the big line. Horizontal asymptotes are easier for end behavior than slants are. You okay with that? Today, I want to add in this piece, like what happens if something cancels out. This is called a hole. And we're going to do this. I think there's some examples in your toolkit. I think there's like 5. We're not going to do them all. I don't think we need to do that many, but okay. So this is toolkit part 3. You'll find this in your green toolkits. I am not going to change anything about the order that I did this problem. I'm going to keep it the same. In your toolkit, I think there's only a blank for the hole. I'm adding in domain and vertical asymptote to your notes because I want to continue to tie that in so you can see that these 3 things work together. On your warm-up, the domain and the vertical asymptote work together. If there's a hole, that works with the domain and vertical asymptote too. Okay? So, if you are presented a problem, you would not know if it had a hole in it just by looking at it. You'd still have to factor the numerator and denominator first. So I'm going to look at this problem, and I'm going to factor the numerator and denominator just like I would in a normal problem. X minus 5, x plus 1, x minus 5, x plus 5. Factor the numerator and denominator when possible. State the restrictions, use them for the domain. I don't want to cancel anything out before I do the domain. Because even if it cancels out, it's still a restriction. Okay? We did that in the first unit. So you don't have a blank for your domain. I'm just adding this in. If you want to add it in, you can. But for my domain, x cannot be 5 or negative 5, right? Based on that denominator. I don't care if it cancels out, it's still a restriction. So the domain for this problem is negative infinity to negative 5 -5 to +5, 5 to infinity. And that's based off of the denominator. Factor the numerator and denominator, state the restrictions, use them for the domain. Cancel out matching factors, use them for the whole. So my next step we haven't done yet. If something cancels out, like this -5 does, when something cancels out, that's called a whole. In this problem, there is going to be what's called a whole at +5. That's an x value, okay? Think about the solution of this one. The restriction of this one was the +5. We okay so far? The way that you will know you have a whole in the graph, you won't see an asymptote there, right? I would think that this is like a vertical line, but you can see from this graph there's only one. If you really looked into the table, you would find an error at -5 and +5, but I don't have an asymptote at 5, okay? So a whole happens when something matches out perfectly. It happens at the x value of the solution, but it's a coordinate point. So we need a y value too. And this part is where like it gets a little, I don't want to say tricky, but there's an extra step to it, all right? What I'm going to do is I'm going to rewrite this problem without the canceled out factor. So this is the same as x plus 1 over x plus 5. I'm rewriting the problem without the x minus 5s. We okay with that? And then I'm going to plug the 5 into the x's. I'm going to plug the value that canceled out into the new equation. So the y value of the whole is 5 plus 1 over 5 plus 5. Or 6 over 10. Or 3 over 5. Or you can write it as a decimal. 0.6 is fine. However you want to write it. Here is how you graph a whole. That is a coordinate point. So you're going to make a point at 5, 0.6, but it's going to be an open circle point. Remember when we were doing piecewise, we had to do an open circle to say like the graph can't go through this point. The graph doesn't go through this point. It's an error, this point. This is the point that will make the graph flow correctly, but it doesn't actually hit the point. So I have to find 5, so 1, 2, 3, 4, 5. This point, I can see it so faintly on my graph, but there's like a little white space. I don't know if you guys can see it, especially far back. There's a little white space where my graph stops graphing for just the smallest second and picks up. It's a hole. You can't always see it, especially if your calculator is in color. It's very hard to see. Okay, so when you're graphing it by hand, you're just going to put an open circle at that coordinate point. It's showing that the graph does this, it does this. It takes a really brief break right there, and then it picks up again. So it's just like a minor pause in the problem. So if the graph has a hole, then that thing that canceled out is not an asymptote. So this particular graph only has one vertical asymptote. It's at -5. You can see it in the graph here. So we do vertical asymptotes after holes. And that can be kind of confusing. So it's factor the numerator and the denominator, find the restrictions. Sometimes kids will cancel out the whole and then not use it for a restriction. So I always say find the restrictions before you cancel anything out. Then if there is a hole, you're going to find the coordinate for that, and then you'll find the vertical asymptote with the new equation. There's only one. All right? You can see holes in your calculator with errors, just like you can see a restriction, but it's not going to show up in the graph as an asymptote. Let's try another one of those. So here's another one. We're going to first factor the numerator and denominator. So I've got x minus 10, x minus 7, and x minus 10, x plus 3. Before I do anything else, I would do the domain. the domain is going to be that x can't be -3 or 10. Because there's 2 factors in the bottom, there's got to be 2 restrictions. So that domain is going to be 3 parts. The domain comes from the restrictions. Normally, the domain and the vertical asymptotes match. I'd say like 95% of the time, the domain and the vertical asymptotes match. The other 5% of the time, there's a hole where they don't match, okay? In this case, there's a hole. It's happening here, right? This is going to cancel out. And so the hole is happening at the x value of 10. Right? The solution of that x minus 10. The y value of the hole you have to solve for. And the way that you're going to solve for it is you're going to take this equation, x minus 7 over x plus 3, the equation without the minus 10, and you're going to plug 10 into that equation. Essentially what's happening here is if I were to type this equation into y1, and this equation here, x minus 7 over x plus 3, into y2, the table would be identical for every single value in all of the tables, except for one. At 10, one of the equations would have an error and the other one wouldn't. Okay, that's the only place they're going to be different. So that's what a hole actually means. It's like, yeah, they're equal except for at this place. This is the only place they're not going to be equal. This equation has this point. This equation has an error at 10. All right, so my hole is at 10, 3, 13. So in my graph, I would have to go all the way over to 10, and I'd make an open circle at that point. 10, 3, 13. So it'd be really close to 0. So my graph will get close to it. It'll skip that 1 point, and then it'll go forever. So my vertical asymptote for this one, there's only one. There's only a vertical asymptote at -3. There's not a vertical asymptote at 10 because it's a hole. You guys think you could try one? I'm going to have you try, see what you can do. This one's a big factor in one. Let's go with this one. So see if you can do D. Find the hole. And if you have time, try the other stuff. Like factor, find the domain, then find the hole, then find the vertical asymptotes. They all go together. So in the factor form, which one cancels out? The -2. That's the one that cancels. The one that canceled out as we're looking. So if you factor this one, your restrictions are x cannot be -6 or -2. -6 being the smaller of the two. So my domain would be -infinity to -6, -6 to -2, -2 to infinity. The vertical asymptote would be the one that doesn't cancel out. The whole would be the one that does. Okay, so in this case, the vertical asymptote is going to be, so the thing that does cancel out is the x minus 2. So you're having a whole at -2. The vertical asymptote is the one that doesn't cancel out. That's the -6. So this error is the vertical asymptote. This error is the whole. You can see that on the graph because the vertical asymptote, the up and down line, the break in the graph is not at -2, it's at -6. Nothing really is happening at -2, so you don't see it, but there is this like little open circle, it's very small, that's happening, that's creating that error. Anybody think they know what the y value of this hole is? What'd you guess, Sean?
45.
I got 0.52. So when you do this one, you're going to take this equation, what's left over after that x plus 2 goes away, and you're going to plug the -2 into it. -2 plus 4 over -2 plus 6. It ends up being 2 over 4, or 0.5. And it looks like on the graph just an open circle at that coordinate point. It's a brief stop. So for your domain, it's like -infinity to -6, break. -6 to -2, it's not as obvious of a break, but it is a break. Like there's an error in the calculator because nothing's happening there. Break, really small break though, and then it picks right back up. What do you think? Whole. All right, so last thing I want to do with you today is just kind of bring it all together. Okay, so all of the effects. We kind of already did this today, so I don't think this should be too painful. I really want you guys to have time to do some practice problems in class. So toolkit, effects of the holes on the domain. I feel like this is probably right after what we just did, and I think for this one the graph's actually there for you, so you can graph it. I'm going to continue to follow my 6-step process over here. So step 1, factor the numerator and denominator. So I'm just going to see off to the side here if this grouping works. So I'm looking for a -6. So 2x squared minus 2x plus 3x minus 3. You might factor using guess and check. That works pretty good for this one too. But again, we're still just factoring. This is factor by grouping. So my numerator is 2x plus 3x minus 1. My denominator is x plus 1, x minus 1. Factor the numerator and denominator when possible. State the domain restrictions, use them for the domain. So even though it's not the next blank, that's where I would go next. X cannot be -1 or +1. That's coming from those two denominators. So I'm going to have to take a break at both of those places. Factor the numerator and the denominator. State the restrictions, use them for the domain. Cancel out matching factors, use those for the wholes. So I am going to cancel out this x minus 1, which tells me that there's a hole at what x value? x minus 1 cancels out. Where's the hole? Close. X minus 1 cancels out. The hole's at positive 1, the opposite of that. So I'm going to have a hole at positive 1. Do you guys see why it's positive 1? I'm taking that restriction of that x minus 1. So that tells me the x value of the hole. To get the y value of the hole, I need to rewrite the equation without the hole in it. And then plug the hole into it. So I just rewrote the equation without the x minus 1s. So that's 2x plus 3 over x plus 1. And then if I know the hole's going to happen at positive 1, then I'm just plugging positive 1 in for all of the x's. And then I just do the math. I end up with 2.5. What that looks like on the graph is at 1, 2.5, there's going to be an open circle. So at the x value of 1 and the y value of 2.5, I'm putting an open circle there. The graph's going to look like it goes through that open circle, but it doesn't. There's a very, very small minor pulse. All right, so we factored, we stated the restrictions, we canceled out, we found the holes. Find the vertical asymptote by setting the factors in the denominator equal to 0. I would normally think there's 2 vertical asymptotes, but one of them cancels out. So this is not a vertical asymptote, it's a hole. The vertical asymptote is the one that doesn't cancel out at -1. So what that looks like is a vertical line at -1. It's kind of like horizontal asymptote and slant. Right? Like if you have a horizontal asymptote, you don't have a slant. If you have a hole, you don't have 2 vertical asymptotes. One's a hole and one's a vertical asymptote. Horizontal asymptotes, I'm still taking those powers. So 2x squared over x squared. So my horizontal asymptote is y equals 2. And if I have a horizontal asymptote, then I don't have a slant. And if I have a horizontal asymptote, then I have an end behavior of the same thing. The horizontal asymptote looks like that. So now I want to put this all together. I'm going to type this equation into my calculator and graph it. So I'm going to do the alpha y equals. Again, you want to set it up like a fraction. And let's see what this equation is. 2x squared plus x minus 3 x squared minus 1. So I'm going to sketch that graph now, and it's going to follow my asymptotes to be a little more accurate. So I'm not going to draw my line through that hole. I'm going to take like a brief break so that you see the open circle, and then it goes after that. So my domain is -infinity to -1, break, -1 to +1, real small break, and then I pick right up again at 1 and continue. I think there's one more with all of it together. So I'm first going to factor everything that I can. And I can divide an x out of both of those. What are the domain restrictions here? 0 and 2. So x can't be 0 or 2. 0 comes first. So my domain is negative infinity to 0, 0 to 2, 2 to infinity. After the restrictions, I would find the whole if there is one. There's not always a whole. Okay, something doesn't always cancel out. A lot of the times you're going to write NA in the whole blank. Okay? But if something does cancel out, like it does here, there's a whole. What x value do you think this whole is? If just x is canceling out. Close. 0. All right, so this is going to be a 0. It's this restriction. Right, the 0 is the one that canceled out, not the 2. To come up with the y value of the whole, I'm going to just write this equation without that x. And I'm going to plug 0 into it. So it's negative 2.5. What that's going to look like on my graph is an open circle at 0, negative 2.5. My vertical asymptote is the restriction that's not the whole. The 0 restriction's the whole, so the 2 is the asymptote. If there's not a whole, then both of them are the asymptote. Okay, so if you don't have a whole, then you've got 2 asymptotes. But we do have one, so the 0 doesn't count. I'm just going to have a vertical asymptote at 2. This is a vertical line at x equals 2. So both of these are the breaks in my domain. For horizontal asymptote, I'm looking at the x squared over the x squared. And they cancel out. So what's the horizontal asymptote here? 1. So I'm going to have a y equals 1. If I have a horizontal asymptote, I don't have a slant. This looks like this. If I have a horizontal asymptote of 1, I have an end behavior of 1, 2. They all tie together. At this point, I would recommend typing this in your calculator and looking what it looks like. However, you'll start to see a pattern. Like, I know if this graph is part of the whole, then something's happening down here. So it's that, and typically when you have that, it's the opposite corner where the other one goes. I don't need you to have that memorized. At no point in this unit am I going to take away your calculator. You can type this in and get this same graph, but I guarantee you that's what this one looks like. So some of you will start to kind of recognize that and not need to pick up your calculator, but you can. What do we think? Hopefully not too bad. I think now, which is different than this unit, is it starts to become more of a routine and a lot of it goes together. So if you're someone who prefers to have like steps, it becomes a little easier. So my recommendation for you, you've got a little bit of time in class. I made this practice / homework, is 2 of these. So 2 of the ones like we just did. Page 5 of your workbook, numbers 4 and 5. Instead of going over it as a class, I just put like the answers on Canvas, but also the explanation. So you're not just looking at a key, you're understanding why the key is what it is. You have the rest of class to do that. If you don't finish it in class, then I would recommend doing it for homework, but it's not something I'm going to check because the keys are on. Okay? If anybody wants me to sit and work on any of those with you, just let me know.